first of all, because we're going to work with the divergence test and kind of complete that. Then we're going to go into what we call the integral test, which is the other main part of the section then, okay? So working with series. Now, one thing that happens a lot of times when you study math, you're always building up to something. So you may be saying series, what's the point? I can give you kind of an idea of where we're going. What you'll eventually find is, like, we can take a number, we can take a trig function. Like, for instance, if you've ever wondered how in the world a calculator figures out the sine of 31 degrees, well, underneath that is a series, okay? It's really the trig functions can be represented as a series, an infinite series, and if you keep adding and adding and adding, you get more and more decimal places. What you're going to end up learning here in a couple weeks is what we call a Taylor polynomial. You'll also end up looking at what we call a Maclaurin series, and that's where you have the ability to take some function and break it up into a series. Logarithms work the same way. If you do a logarithm of 2 on your calculator, you get a bunch of decimals that repeat forever. Where does that come from? It comes from a series. So we have the ability to break things up into series. Even the number pi, there's a way to break that up into a series. The number e, you can break it up into a series. So that's what computers are doing when they're figuring out all those decimal places. So they're doing a series, okay? That's it. That's how we can get further and further and further decimal places. Does that make sense? So at least that gives you an idea of kind of where this is going, okay? So what we're doing with the divergence test is, the key thing is anytime that when you're learning all these different tests, always refer to what the test says, okay? So what this is saying is, if your series is converging, then that means the limit of the sequence is 0. That's a given. So once you've established that the series converges, then you know for an absolute fact that the limit of the sequence as k goes to infinity is 0, okay? But it doesn't work the other way. So the other way that you can look at this is, if the limit of the sequence is not equal to 0, then it diverges, okay? So as you're doing these tests, make sure you're very clear on what the divergence test says. So this is essentially what you're going to do. When you do the divergence test, you're going to work with the limit of the sequence, okay? That's the part that's part of the series that you're adding up, okay? So if it's not equal to 0 or doesn't exist, then it diverges. That's a guarantee. If it goes to 0, then you can't conclude whether it diverges or converges. So what you generally have to do on that is you have to go through a different methodology, and you have to investigate it further. And there's all kinds of different tests that we're going to learn. So that's kind of the idea. All right, so let's go in. I think we're ready to go to the next page in number C. So I'm going to do a couple other problems where you're working out the divergence test, okay? So here's what you're going to do. If you're asked to do the divergence test, first thing we want to look at on this one is, you don't have to do this, but I like to do this as I'm teaching some of those. Let's just write out maybe 3 terms. Okay, if you're doing this series, if k is 1, you would have square root of 1 squared plus 1 over 1. Then you would go to the next term, so it would be 2 squared plus 1 over 2. And then it would be 3 squared plus 1 over 3, and so forth like that. So what am I doing? I'm just varying k. K is right here. If you look at what I did, k is right there, and it's right there. It's just going 1, 2, 3. So what we're trying to do on this is we're trying to figure out, if you summed all of those terms, the infinite number of terms, does it converge to some value, or does it just diverge? It doesn't go anywhere, okay? If you work this out a little bit further, this would be, I'm going to do this in my head, that's square root of 2. This is square root of 5 over 2. This is square root of 10 over 3, and so forth like that. So at first glance on that, it's kind of hard to tell whether that's going to go anywhere. I don't really get a good sense out of that. So what we're going to do when we do the divergence test, what you're going to do is you're going to do the limit as the variable k goes to infinity of the sequence. The sequence is that part right there. So we're going to work out the limit of the square root of k squared plus 1 all over k like that. Now, let me show you how you could reason this out in your head. Okay, I do like you guys to show the algebra behind this, but here's how I reason this out in my head. When you get to infinity, the 1 makes very little difference. Agree? Okay, so if you block that off, what do you have? Don't you just have a 1 there? Okay, you have square root of k squared is k, k over k is 1, so that's going to be 1. You can do that in your head. Now, what I'm going to do is I'm going to do this more algebraically because you have different techniques. Technically, this is an infinity over infinity limit right now. You could do L'Hopital's rule, but it's probably better if you go this way. So we already know that it's going to go to 1, but let's go ahead and do this way. So what I'm going to do is we're going to divide by the highest power. That's the typical thing we do. So what I'm going to do is actually that power right there, if we want to go under the radical, we have to multiply by a radical. So I'm going to multiply by 1 over k squared, okay, to get rid of that power right there. And then I have no choice but to do exactly the same thing on the next thing like that. Okay, so you can just think of going under the radical and dividing by k squared. Okay, now when you do this, then what you're going to have is you're going to have the limit as k goes to infinity. Underneath that square root, okay, just think about distributing. So that's going to be k squared times 1 over k squared. So that's going to be 1. And then this times this is going to be 1 over k squared like that. Okay, when you do the denominator, just look at what you're going to have. You really are going to have k times 1 over k. So that's going to give you a 1 like that. Okay, now look at that and tell me if you understand what I did there. The reason that I had to multiply by a square root of 1 over k squared is I got to get that under that radical. So that's got to be in a radical within itself. Okay, so what I have is this, and then the limit would be k goes to infinity. We're going to work out the limit of 1 plus 1 over k squared like that. Okay, now here's what happens. Okay, we're going to let k go to infinity. So can you see now in your head that that's going to go to 1? What is 1 over k squared going to go to? That's 1 over infinity, right? So where's it go? It goes to 0. So square root of 1 is going to be 1, so that's the answer to that limit, okay? So what you would conclude then, if you look at your divergence test, if it's not equal to 0, if the limit's not equal to 0, you're going to conclude that it diverges. So what you would say on this is you would say, since the limit k goes to infinity of the sequence k squared plus 1 over k is equal to 1, then you would say it diverges by the divergence test, like that. Okay? You want to kind of get in the habit of stating your conclusion. There's a reason why it diverges, okay? When you get to your third exam, I'll tell you, it's going to be lots of these tests, and probably over half of the problems, the answer is either going to be converge or diverge. But it's not like a lucky guess, okay? You got to prove to me why it's doing that. So this is why, is because you have to state something like that and show that that limit turned out to be 1. That's why it diverges. Does that make sense? It's incredibly important. You can't just take a wild guess, all right? Okay, so that would be kind of how that one goes. Does anybody have a question about what I did there? Okay, the next one has a factorial in it. So a factorial is something you may not be familiar with. So let me kind of introduce you to that idea. Whenever you see this exclamation point, like for instance, maybe you've seen this in your background, maybe you haven't. Not all students have. What it means is, it just means you take the first number and then you multiply, you just go down until you hit 1. So 3 factorial would be 6, okay? If you had 5 factorial, that would just be 5 times 4 times 3 times 2 times 1, whatever that is, okay? All right, so I think that is 120 is what that is, okay? And if you have 1 factorial, that's 1. And 0 factorial is 1 by definition. And we're going to get into that and start seeing that more and more. So I just want to give you the idea what that is first of all. Okay? All right? now what I want to do on this one is let's write out some of the terms on this, okay, just to get started before we do the divergence test. So when k is 1, you're going to have 1 to the third over 1 factorial. Okay, then you're going to go to k equals 2. So you'll have 2 to the third over 2 factorial. And then you would have 3 to the third over 3 factorial and so forth like that. Okay, so what's happening on this, if you went ahead and calculated this, this would be 1 over 1. That would be 1. This would be 8 over 2. So that would be 4. This would really be 27 over 6, because 3 factorial is 6 like that. And then it would go on forever and ever and ever and ever like that. Okay? So what we're going to do on this is we're going to kind of get a sense of whether that infinite sum diverges or it does come down to some answer and has a finite sum. Okay, that's the idea. Okay? Does the factorial, everybody understand what I'm doing there? Okay. Okay? All right? Now, if you ever need to do a factorial, let me just explain where this is on your calculator. So you might not know this because usually students, this shows up in statistics a lot. In a branch of mathematics called combinatorics, it shows up quite a bit. So if you look at your math button, you go there. And then if you go to your probability menu right there, you'll see a factorial button, option 4. That's the way it is on my calculator. So again, that's math, probability, option 4. So if you wanted to do 9 factorial, you just type a 9 in, then you go math, probability, option 4, and it gives the answer for you, okay? And I want to show you this because I want to give you a sense of what happens. I'm going to put in like 80 factorial and show you what happens. So I'm going to go 80 math, probability, option 4, 80 factorial. Look at this. Look what happened. It overflowed. This calculator is not powerful enough to do that. So that means it's humongous. Factorials get out of control big very, very fast, and that's a big deal on this problem. Okay? So when we do the divergence test, here's what we're going to do. We're going to do the limit as k goes to infinity of k to the third over k factorial, okay? Now in this problem, you really reason this limit out in your head, you really do. But what I'm going to do is let's just write this out one more step to help you catch on to this. K to the third is just k times k times k, all right? When you do k factorial and you want to get comfortable with how you write this out, what you always do on a factorial is you always write down the first term. Okay, so if it's k factorial, that first term is just k. Then you do 1 less, right? So the next one's going to be k minus 1. Then you do 2 less. So that's going to be k minus 2 and so forth. And that's going to go on and on and on forever like this. All right, so let's think about what's happening on this problem for the limit, all right? So really we have an infinity over infinity limit. If you plug in a k, you have infinity there. You have infinity here. Okay, tell me which is bigger, the numerator or the denominator? I mean, they're both infinity. Actually, in this one, the bottom gets way bigger. Because see, what you're doing on this is you're always just taking k and multiplying it 3 times. But what you're doing here, see how you have a k infinitely? K, k, k forever. Okay, that would be like k to the n. Okay? So this is like way bigger in the denominator, so what would the limit be? It'd be 0, right? Okay, does that make sense? Okay, because that denominator gets out of control. I mean, it's way bigger than the numerator. Yes?
I just didn't get it. Why would you write the denominator like k to the parentheses k minus 1 and k minus 2?
Okay, that's kind of how a factorial works. Like, use this example. When you do 5 factorial, what do? You write down the first term, which I did. Okay, then how do you get the next term? 5 minus 1, k minus 1. How do you get the next term? 5 minus 2. And then forever and ever and ever like that. Okay, that's the idea. All right, so that limit's going to be 0. Okay, so that's what we get. And just kind of think of it in that regard, so we'd end up having the limits equal to 0. Okay, does that make sense? That the denominator is much bigger than the numerator. Yeah.
Well, if you would encourage that the denominator will be bigger than the numerator. Can you do another way?
You could if you started going through it, you couldn't really divide by the biggest term. L'Hopital's rule that'd be really complicated. So it's really more of just an idea that if the denominator is bigger than whatever that is, much bigger than that, then that limit's going to have to go to 0. Okay? All right? The idea is when you get out, like if k was 100, just think if k was 100, then you would have 100 times 100 times 100 over 100 times 99 times 98 times 97 blah, blah, blah times 1. So do you agree that the denominator is much bigger than the denominator? In fact, if you did 100 factorial on your calculator, it'd overflow. Okay? All right. So that's the idea. Okay, so what do we get out of this then? If the limit is 0, what do you conclude? You conclude that it's inconclusive. Okay? So we say that it's inconclusive. That means we don't know whether it diverges or converges. We could figure it out with other methodology, but the divergence test won't do anything for us. Okay, so that's the idea. All right, does that make sense? Okay, so you're doing limits. Okay, you got a strong background for limits now. So you're doing a limit and you're seeing if it's 0 or not 0. That's kind of the key on that test. Okay, all right, so now we're going to introduce the integral test. All right, so the way this works, we don't prove these things in these classes, we just give these. If you study math at a higher level, like take analysis and stuff like that, like if you're a math major, then you study this at a much more in-depth level. So the integral test, what this is saying, basically is this. Now, one thing that's important is the integral test, you can only use it in a certain situation. So your function has to be continuous. You always want to make sure that it's continuous on the interval you're interested in. Doesn't have to be continuous everywhere, just where you're interested in. All the terms have to be positive, and it has to be decreasing. Okay, so it's got to go like that before this integral test will work. And you're looking at x is greater than 1, and the reason you're doing that is typically you're gonna start your series at k equals 1. That's the reason you do that. Okay, so here's the idea. If you're trying to investigate an infinite series, k goes 1 to infinity, then you can translate this into an improper integral. Okay, remember a series is a sum. Isn't an integral also a sum? Yeah, it's a sum of an infinite number of tiny rectangles, right? That's what you learn. So they're both infinite sums, so they mean the same thing. So we just say integral 1 to infinity of whatever the function is that's modeled by that sequence. That's the idea. So here's the key. It turns out that if you can figure out what happens on the improper integral, which you already have a background for doing it, then you can make this conclusion. So what it says is both of these things either converge or diverge. So if you figured out the integral converged, then what would you conclude? Therefore, the series converges. If you figured out that the improper integral diverged, what would happen with the series? It also diverges. Okay, does that make sense? So you investigate the integral, and whatever its result is going to be the result of that series. That's how that works out. That's what the integral test is essentially telling you. Okay? Now, the other thing is, this is kind of important on this, the value, so say for instance that your integral turned out to be a number like 2. That does not mean that the series is going to add up to 2. And I'll tell you why that's the case is because a function has an infinite number of points on it, right? A sequence does not have that. It's what we call discrete terms. It's just pieces of that function. So they don't necessarily go to the same number. Okay, so that's the idea. So you want to get in your mind that you want to look at the improper integral and determine whether it converges or diverges. Okay, that's the idea. Okay, so let's look at some of these and kind of show you how this goes. Well, the key on this is how good are you with improper integrals. That's one of the reasons you learn improper integrals is because it's a part of investigating series. Okay, So the first thing is we're going to look at this infinite series like here. Now let's write a few terms out just to kind of see what's going on. So if you did plugged in 1, you'd have 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1, and so forth forever and ever and ever like that. Okay, well, one thing I can see by this, and you can see this too, is what's happening to the denominator. It's getting bigger, isn't it? What's the numerator doing? It's staying the same forever. So as you go way out there, you're going to have 1 over something infinitely big, right? So that sequence, the limit of that sequence is going to go to 0. And what that tells you is it's inconclusive. Since that limit goes to 0, we don't know if it diverges or converges. Okay, now I do have a typo all over the place on this handout. I just noticed this. We're not doing the ratio test. We're not there yet. We might get there today. This is supposed to say the divergence test, okay? So if you basically did this, if you did the limit as n goes to infinity of 1 over n squared plus 1, that goes to 0. You do that in your head, okay? That's an easy one to just do in your head. It's 1 over infinity is the form on that, so 1 over infinity is going to 0. Okay, so what we're going to do is we're going to do the integral test. So since that's 0, that means that that's inconclusive. We don't know yet if it diverges or converges, so we're going to go to the integral test if it applies. Okay, so the first thing is we're going to represent this by a function, and we're just going to change the n to an x. Okay, we're just going to look at 1 over x squared plus 1. We're going to look at that function. Okay, first thing you got to do is you got to make sure that you verify these conditions. Is it continuous? Well, is there any place where this function is undefined? Is the denominator ever 0? No. Okay, so that's a check mark. Yes. Okay, that's a condition for the integral test. Are all the terms positive? Look at my first 3 terms. Are they all positive? Are they ever going to change? No. That's also a yes. Okay, decreasing. And sometimes you can get a sense of this just by looking at this. So for instance, this is like 1/2, 1/5, 1/10. Are the terms getting smaller? Yes. Okay, that's good enough. If you can see it, that's good enough. So it looks like all those things check out. Okay. So then what the integral test tells you to do then is what we're going to do is we're going to do an improper integral. So we're going to write the integral from 1 to infinity of 1 over x squared plus 1. That's an improper integral that we should be able to do okay, all right? Now on your exam too, I noticed that there was 3 improper integrals on the test. You guys did well on the first 2. The one you didn't do well on was the one that had a vertical asymptote in the middle, where you had to break it up into 2 integrals. So as we go through this, you'll probably get stronger with your improper integrals. Okay, what do you do on this first of all? What do you need to change that to? A limit, right? So you need to change this to a limit. Anytime you got an improper integral, you're going to say the limit. We're going to say 1 to b. And what are you going to do with b? You're going to let b go to infinity. Okay, then you have 1 over x squared plus 1 dx like that. Okay, so we're ready to go. All right. Do you know what the antiderivative of 1 over x squared plus 1 is? That's the inverse tangent. Okay, that was easy. That's kind of nice. Okay, so what we're going to have is the limit as b goes to infinity of the inverse tangent or arctangent, whatever you prefer, going from 1 to b. One thing I noticed on your test is a lot of students would go there, but then they wouldn't evaluate the b and 1. You got to do that before you do the limit. So what you got to do is the limit as b goes to infinity, and then we're going to do inverse tangent of b minus inverse tangent of 1 like that. Okay? So we need to do that. Well, so what is, hopefully you know this from trigonometry, what's the inverse tangent of 1 in radians? Pi over 4, right? At pi over 4 on a unit circle, when you have pi over 4, where are you? You're at the point root 2 over 2, root 2 over 2, right? The tangent's y over x, so the tangent of pi over 4 is 1. Okay? And the range of an inverse tangent is negative pi over 2 to pi over 2. Okay, so what you're going to have now is you're going to have the limit as b goes to infinity of the inverse tangent of b minus pi over 4, like that then. Okay? All right, now what we need to do is we're going to go ahead and evaluate it at infinity now. So if we do this, we're going to have the inverse tangent, and I'll just put an infinity there, minus pi over 4. Okay, now it's trig background stuff here. Okay? All right, the inverse tangent, okay, you know the graph of the tangent does this, right? What does an inverse tangent graph do? Does this, right? Okay, so an inverse tangent's graph actually kind of looks like this. It goes like that. All right, so if you're doing the, if you're going out to infinity, that thing's approaching a horizontal asymptote. You remember what that horizontal asymptote is? Pi over 2. Okay, look at your unit circle if you have to. These are things you got to review every now and then. So that's going to be pi over 2 like that then. Okay. All right, so what we would end up having then is you're going to have this situation then. So we're going to have pi over 2 minus pi over 4. Okay, so that would be like 2 pi over 4 minus pi over 4. So that's going to be pi over 2. Okay, so that's what we have. Okay, so what does that tell us then? All right.
Pi over 4. Yeah.
Oh, pi over 4. Yeah, pi over 4. Okay, see how I do all this stuff and I do something stupid like that? Okay. All right, that's because I was whipping through the arithmetic. I always get kind of out of control on that sometimes. Okay, so what did we find? This converges, right? Okay, it converged to a value. So then we're ready to write a conclusion on this. So it did come to a value. So here's our conclusion. Since this converges, okay, so does this. Okay, that's what you're doing with the integral test is whatever you get on the improper integral, that will apply to the series. Okay, and the reason is they're very similar. Try to make yourself understand this too. One thing I did, and I don't know if I put this on your handout, I graphed this on my calculator, and this is what the graph of 1 over n squared plus 1 is. So if you were doing that improper integral, you were actually finding the area under the curve, okay, from 1 to infinity, and that area under the curve is pi over 4, okay? Now, let me ask this question, because this is important. Does that mean that the value of that series is pi over 4, yes or no? No, okay? Here's why. A series is not all of those points. It's just points at integers, 1, 2, 3, 4, and so forth. So the graph of that series is not continuous. It's like little dots. Boom, boom, boom. It can't be the same. Does that make sense? It's got all those places that are different. So it's going to sum up to something different than pi over 4. Okay? Okay, how's that problem look? The vast majority of what I did is something you've already done, right? Integrals. Improper integrals. That's what you're going to do on the integral test, okay? All right, so let's do some different situations here. Okay, so looking at next page here, so we're going to look at this one. We're going to go ahead and do a divergence test first of all. So on a divergence test, what do you do? Limit n goes to 0, not 0, to infinity, 3 over 2n minus 1. Okay? A lot of times you just do this in your head. What's the value of that limit? 0. Everybody solid with that? How come? 3 over infinity, right? The denominator is infinite. The numerator is 3. Okay? So by the divergence test, remember, if the limit of the sequence is 0, the divergence test is going to tell you that we're inconclusive. Now, the reason I keep doing this divergence test is if we got diverges as our result of the divergence test, we're done with the problem, so you can forget the integral. Wouldn't that save you a lot of time? Yeah, okay. So that's a good place to start on a series, is to look at the divergence test. Okay, so the function we're going to use, we're going to move on to the integral test. We're going to work on 3 over 2x minus 1. Now let's think about the continuity. You always need to make sure you verify these things. Don't just jump into your integral, because it may not even apply. Is this function ever discontinuous? Is the denominator ever 0? Yeah, it is. Okay. It's discontinuous at one place. So if you did 2x minus 1 equals 0, and if you solved that equation, you would get a problem at 1/2. However, that's not a big deal. You know why it's not a big deal? Because where does the series start? It starts at 1. So we don't care. It's okay that it's discontinuous at 1/2. So the answer is yes, it's continuous on the interval 1 to infinity, and that's good enough for us. All we care about is wherever the series starts. So the 1/2 doesn't have any bearing on anything. Okay, does that make sense? Okay, now let's look at the terms are positive. Well, what you want to do on this, and you can oftentimes just do this in your head, one thing that you can do is, like, if you, and you don't have to write this down if you don't want to. I'm just going to plug in a 1 and then plug in a 2, plug in a 3. Yeah, there we go. I'm doing that kind of fast. So that would be 3 over 2, 3 over 5, 3 over 8. Have I got that right? I think I do. Okay, so the terms look like they're positive always. Yeah, okay. So you just kind of look at the terms and kind of get the general strategy. What's happening is the numerator is always 3. That's not going to change. And you can tell the denominator is just going to get bigger and bigger and bigger and bigger forever. Now what's going to happen is you go way, way, way out in this series, you're going to have 3 over infinity. Agree? Okay, the denominator is going to get bigger without bound. Okay? All right, so we have that. Now if you look at the terms are getting smaller. Okay, everybody agree with that? They are decreasing. Okay, each term is getting smaller. So you can just kind of look at that. All right? Okay, so that means that we're ready to go through and look at the integral test. So what we want to do next is let's get going on the integral test. So what we're going to do is the improper integral 1 to infinity of 3 over 3x minus 1. You want to change that variable to x because we're dealing with a function now. Yes?
It's 2x minus 1.
It's what?
2x minus 1 on the denominator there.
Oh, you know what I did? I think I wrote over that so I couldn't see what it was. Thank you. Okay. That changes, you know what that does? That changes the values of this. So I guess it would actually be, if that's a 2, that would be what? 3 over 1. That would be what? The next one would be 3 over 3. And then that would be 3 over 5. Well, same thing, right? Doesn't matter, okay? We still know we can use the integral test on that then, okay? Okay, so let's kind of go through and think about this. Okay, we have an improper integral. It's important that you immediately change this to a limit. So we're going to say limit is b goes to infinity of the integral from 1 to b of 3 over 2x minus 1. Okay, like that. Well, let's see. What could you do with the 3 if you wanted to? You can pull it out. That's a constant. It can go outside of all the way out of the limit. It can go out of the integral and out of the limit also. So let's just have 3 times the limit as b goes to infinity of 1 to b 1 over 2x minus 1 dx. Okay. Now that integral right there is probably a logarithm. It's probably a natural logarithm. And you probably need to work with a U-substitution. Sometimes these integrals you can do in your head. I'm going to go ahead and just do this by U-substitution. Okay, so I'm going to let u be the denominator. Okay, 2x minus 1, that's going to be the u. Okay, then du is going to be 2 times dx. Okay, so if I divide both sides by 2, I'm going to get 1/2 du equals dx. Okay, so the dx is going to go to 1/2 du. Okay, this is what a lot of you didn't do on the test. A lot of you just forgot all about changing your limits. Okay, and most of the time when you're doing a U substitution, it's not a bad idea to change your limits. Get it out of the way. Okay, so let's do that. the U-Substitution is given by U equals 2x minus 1. Okay, so let's work on the limits. Let's do that too. So if your lower limit is 1, then this is going to be 2 times 1 minus 1. Well, that's going to stay 1. So that just stays the same. Okay, if you plug in a b, that's going to be 2b minus 1. So I'm going to go ahead and change that like that. Okay, so I'm going to go ahead and just do the u integral and be done with it. Okay. All right, so when I do this, then I'm going to have 3 times the limit. B goes to infinity. I'm going to go from 1 to 2b minus 1. And I'm going to have this. I'm going to have 1 over u times 1/2 du like that. Okay, so that's getting everything plugged in. We got everything absorbed. And then we're ready to move with this integral and get this done. Okay? Everybody with me okay? Okay, this is a pretty simple integral. This is not one that you should have any trouble with, hopefully. Okay, so what I'm going to do here is I'm going to go ahead and take that constant out. Okay, so I'll have like 3/2 times the limit. B goes to infinity. Now let's just think about this integral right there. Well, that integral right there is a natural logarithm, right? So what you're going to have is you're going to have the limit of the natural logarithm of u evaluated from 1 to 2b minus 1. Okay, like that. Okay, evaluate your integral before you do the limit. So when we do this, we're going to have 3/2, and then we're going to have the limit. B goes to infinity. We're going to have ln of 2b minus 1 minus ln of 1, like that. Okay? And then we'll be ready to go through and evaluate that limit then. Okay? All right, any questions so far? Is that improper integral looking okay? See, remember I changed those limits. Do that. Okay, I mean, it usually makes it easier. See, we're done with the integral, okay? All right, so what we'd have now, if you plug in infinity, you can do this in your head too. That would be 3/2. That's really just saying ln of an infinitely big number. You're doing 2 times infinity minus 1. That's infinity. ln of 1 is 0. So what does that do? Converge or diverge? It diverges. How come? ln of infinity is infinity. It gets bigger and bigger and bigger. A natural logarithm graph looks like that. It gets bigger forever without bound. Okay? So that is going to diverge. So that means we've got the conclusion we're after. So what we would have then is, since the improper integral diverges, what does that tell you about the series? Same thing. That's what the integral test teaches you. Okay? Problem done. Okay? So that's it. So that thing right there, if you took a supercomputer and crunched out that series with billions and billions of terms, it would never be coming to a certain value. It'd just get bigger forever. Ever and ever. Okay? It would slow down, but it would get bigger without bound. Okay? All right, any questions on that? Okay, so integral tests, we're going to keep kind of going through some different things here. And, you know, the whole idea on this is going to be integrals, so you got it. This will help you get better with your integrals too as time goes by. So let's go ahead, and I kept cutting and pasting ratio test. Again, that's supposed to say the divergence test, okay? So let's go ahead and let's look at just a few of the terms on this, and I'm going to do this kind of at the side. I recommend you do this in general when you're looking at a series, is write out maybe 3 terms. So I'm going to just start with one. I would have ln of 1 over 1. Then it's real simple. ln of 2 over 2. ln of 3 over 3. Forever and ever and ever and ever again like that. Okay? Now, if you look at this series, let's think about what's happened. Obviously, the denominator is getting bigger forever. How about the numerator? Is it getting bigger forever also? Yeah, because you're doing an ln of a bigger and bigger and bigger number. So you kind of get, when you go way out here, you know, you've got the numerator's infinity, the denominator's infinity, but you really can't really tell by writing that out what's going to happen on that. That's not enough. But it does help you with these 2 things. First of all the terms are definitely positive. There's no doubt about that. because you're doing a logarithm of a positive number, you're going to get a positive, okay? Now the next thing is what's happening on these terms. Well, the terms are decreasing. I'm going to do a little bit more with this problem also. I'm going to go into a little bit more detail with the decreasing. So it looks like it's decreasing, but I'm going to go further into that because I want you to do this on some of the problems. Okay, so if you like crunch those out on a calculator, you would begin to see that every term is getting smaller. The denominator is getting bigger, and so is the numerator. But what's happening is the denominator is outpacing the numerator. It's getting bigger faster than the numerator. Does that make any sense? Okay, that's the idea. Now, I'm going to remind you of something you learned in Calc 1. Okay, you learned how to tell if something's decreasing or increasing in Calc 1. I taught that yesterday in Calc 1. Okay, we're working on that. Well, the way you do that, if you want to investigate the decreasing, you try to figure out where the derivative is negative. And I'm going to go ahead and do it on this problem, okay? Sometimes you need to go a little further because it might not be obvious to you that those terms are, that the function's really decreasing. So let's do that, okay? Let's go ahead and do the derivative of this function. Okay, the function is going to be ln of x over x like that. We'll talk about the continuity here in a minute. Okay, let's get this done. So let's do the derivative. So if f of x is ln of x over x, that would be a quotient rule, right? So let's go ahead and do the quotient rule on the derivative. So that would be bottom derivative of top is 1 over x. Minus top, derivative of bottom's 1, all over bottom squared. That'll cancel the x out. That'll leave 1 minus ln x over x squared like that. Okay. Now what I'm going to do on this is I'm going to set this equal to 0. X has to be a positive number. You can only take a logarithm of a positive number. So I'm going to set that equal to 0 to get a critical point. So if I multiply both sides by x squared, I'm going to get 1 minus ln x is equal to 0. Okay, like that. I can move the logarithm to the other side, and what I would get is 1 is equal to ln of x. Okay, what's the answer to that equation? What? E to the first. Okay, yeah, okay, that's e. Exponential form, so you'd say e to the first is equal to x. Okay, like this. Well, what you learned how to do in Calc 1 is you end up making a sign chart on this. So first of all, you got to start at 0 because that has to be positive. N has to be positive. Okay, and our sequence or our series is only going from 1 to infinity. So really we just got to start at 1. That's all we're going to care about is that what's going on at 1 because that's where the series starts. Okay. E is out here. E is about 2.7, so you do that. So what you would end up doing then is you would end up going through and you would do test points into that derivative. Okay, so if your derivative is, let's see, our simplified derivative was 1 minus ln x over x squared. Okay, so like if you took like a number, not there, between 1 and e, like if you took 1.5. If you plugged it in there, what you would end up getting is you would actually end up having this kind of situation. So if you took like your calculator if you needed to, and if you did like this, okay, if you did 1 minus the natural logarithm of 1.5, uh-oh, oh goodness, I was kind of whipping through that derivative. I think I did that okay. Oh my goodness. I'm going to go out and do one more thing here. Yeah, okay. Let's do 1 minus ln. There we go. Okay. It's going to end up decreasing probably after e, which will be okay. All right. So what'll happen with this then is if you did this sign chart, I think it's going to end up having a plus, and then once you go out there, it'll be negative. Let me show you what I mean by that. So if I was to go through and graph the, shoot, let me get this in the right mode here. I'm going to graph the derivative, so I'm going to put this in, okay? All right, so let's see. The derivative is, we got 1 minus, let's see, ln of x, and then divide by x squared. Now, see, I know the denominator is always positive, so I've got that. And I'm just going to do that from, I'll just do a standard window, okay? And just take a look at this for a minute. Okay, so what's happening on your derivative? If you look at this, I'm going to zoom in because you'll see this a little better, okay? And it turns out that what's going to happen on this derivative is you have positive values there, right? So on the sign chart, you would actually be increasing, but then once you get past e, you're going to see that, if I zoom out, you'll be able to see this a little bit, somewhat. You'll be able to see that this thing, once you get to e, which is right there, it starts going below the x-axis. So your sign chart's plus minus, so what it's doing is it's going to be increasing just for a little bit, then it's going to be decreasing. So as long as you go out in the series and it begins to start decreasing from then on out, then you're okay. All right. Now what I did I put this graph on your handout? I don't remember. Okay. So this is actually the graph of ln n over n. Okay. So here's what happens on this. That's e. You can tell that it increases until it gets to that maximum, then it decreases like that. So there's a couple of approaches, okay? Sometimes when you're verifying whether it decreases, you can look at your terms and just see that way. The other way is to do this kind of thing like you did in Calc 1. A third way is just look at it on your calculator, okay? That's the easiest way to do it fast, is look at your calculator. So everybody understand that although it increases for a while, once you get past e, it's decreasing from then on out. That's what matters, okay? So we are okay with that. Okay, is this function continuous everywhere? Is there any place where ln x over x is undefined? 0. X can't be equal to 0. Does that matter on our series? No. How come? Series starts at 1. Good, okay? So we're all good and we're ready to go with the integral test. Okay, I like to kind of remind you of how to do that decreasing test like from Calc 1, because that's something that you need to do sometimes. But when you're doing your homework, you can use technology to you can just graph and you can make sure that it's decreasing, because I think it's always a good idea to do these on a graphing calculator anyway, to get a sense of how the function looks. Okay, all right, so we're ready to go with the integral test. So let's go ahead and get that set up. So we're going to do the integral from 1 to infinity of ln, whoops, not n, we want to change this to x, so we want to have ln of x over x, okay, times dx like that. Okay, so you want to go ahead and write this as a limit, so we're going to do the limit as b goes to infinity of, from 1 to b, of ln of x all over x times dx like that, okay? And now we got to do the integral. What is that? What kind of integral does that look like to you? U-substitution. Always start with U-substitution. Don't just jump into parts. Okay? What you can do on this one is you can do this. If you let u be ln of x, then what's du? The rest of the integral. See, that's just a real simple one. So you jump into parts, you may just be wasting your time. Always look at U-substitution first before you go to the next ideas. Okay, so we're good there. Now let's do the limits. Don't forget to change your limits. Okay, so let's start with 1. So we're going to do ln of 1. And let's see, ln of 1 is 0. So that limit right there, that's going to go to 0. Okay, ln of x is going to go to u. And then dx over x is going to go to du like that. Okay, let's do the same thing with b. So that's just going to go to ln of b, like that. So we're now ready to do our u integral. Okay. All All right, so we're going to have the limit as b goes to infinity. Now we're going to go from 0 to ln of b. When we changed that limit, that went to ln of b. Okay, so we got that. And then we have, let's see, what do we have? U du, right? Okay, so we have ln, we let u be ln of x, so that's going to be u times du like that. Okay? All right, so let's go ahead and get that worked out then. So when we do this, we're going to have the limit. I'm going to keep bringing the limit down because I don't want to forget to do that. So that's going to be, the antiderivative is u to the second over 2, and that's going to be evaluated from 0 to ln b like that. Okay? And then from here, we're ready to evaluate the integral. So that's limit b goes to infinity of ln b squared. And you can bring that 2 out. That's a 1/2. So if you want to do that, that's what I'm going to do. You don't have to, though. So I'm going to bring that out as a 1/2, like that. And then we're going to plug in the 0. So we'll have 0 to the second, like that then. Okay? All right, so let's see what we have then. So we have 1/2. We can go ahead and plug this in now and get this result. So we'd really have like ln of infinity squared minus 0. Diverge or converge? Diverge. The whole key is this thing right here is infinite, right? When you do the ln of a bigger and bigger number, it gets bigger and bigger without bound. Okay? So we're ready to draw our conclusion. That's going to diverge. Okay? So therefore, you got your conclusion. Okay? So since the integral diverged, then the series also diverges like that. That's how you know that. Okay? Okay, you guys follow everything on that improper integral. Okay, that's the key. Now, you'll find as we study series, you're going to find when you do your homework, the integrals are going to be probably most of the time easier than the real bad ones that you've done. Okay, just kind of works out. Not always, but you'll see that. So you want to kind of get to the point where an integral like that needs to be a piece of cake for you. Okay, nothing to it. Okay, all right. So let's see. Let's move on and let's do, I think I want to go ahead and do a couple more things, then we'll do a break. Let's go ahead and do these next 2 problems on this page, and we'll break after that. Just kind of get a sense for how this goes. Okay, so when you're looking at this, let's kind of start with the divergence test. So when you do the divergence test, you want to do the limit of k goes to infinity of the sequence k over square root of k squared plus 4. Okay, and if you can do it in your head, do it in your head. Here's the way I look at this problem. Okay, hopefully you guys are down to this point where you're starting to just try to see if you can do this in your head. When you're at infinity, does the 4 make it much difference? Not really. So what is that going to go to? 1, right? Okay, you got k over k, really, right? So it goes to 1. Everybody follow me on that? Okay? So you can just go ahead and write the conclusion if you want to. Okay? When things are fairly simple like that, I want you to do it in your head. Okay? You don't have to use L'Hopital's rule and divide by the highest power. You can, but if you can do it in your head, just do it. Okay? So anyway, what that means is on this one is, okay, we've already got the answer, don't we? Okay, so basically, if that's not equal to 0, then that tells us that we're going to diverge. We're already done. Okay, so the problem, we could actually just stop here and say, okay, we're done. All right, we got it. So I'm going to go ahead and I'm going to do the integral test on this just for the practice of that, but we know the answer. Okay, everybody follow me on that? So when you're doing your homework, okay, don't forget about that divergence test. Don't just jump into the integral test because sometimes, boom, you're done. Look at that. Problem done in 10 seconds. Okay, so I want you to be able to do that. Okay, well, let's go ahead and do the integral test for the practice of that. The function is going to be x over square root of x squared plus 4. This function is always continuous because the denominator is never 0. If you have x squared plus 4, you're never going to get a 0 out of that because you're squaring x, okay? The terms are going to be positive. If you write them out, the terms are going to be positive. And the other thing that I wanted to look at on that is if you looked at this, now see, you could do this. I'm going to just do this on the calculator real quick to get a sense of what's going on. So if I put the function in x divided by square root, let's see, x squared plus 4, just to see if this function is generally decreasing. Let's see kind of what I got here. And I'm just going to do standard window, okay, like that. That's kind of interesting. Now I'm going to change my window just a little bit here. I'm going to start at 0. I'm going to go out to like 100. Scale maybe by 10 or something like that. And then the minute y, I'm going to go 0 to 1 or something like that. And just see what we get here. What do you think? Looks like it may increase. So it may look like the integral test may not even be applicable on that. Okay? So what you would end up having on this is you would end up, it looks like that part right there is going to fail anyway. So it looks like we couldn't use the integral test on this. Okay? So what we would end up getting for a conclusion is we have this. Okay? So we don't need to do the integral test on that. All right? Now, the other thing that you could do, see, sometimes you don't want to go by your calculator. If you actually went through and did the first derivative and did that sign chart like you did in Calc 1, that's the only way to know for sure if it's ever going to decrease forever. But that's the idea. Okay, yes?
I did the integral anyway, so I got diverge. Is that just by luck, or is that?
Yeah, well, yeah, the integral test wouldn't apply to that. But, yeah, I mean, it just happened to work out that way. Yeah, okay. All right. So see, save yourself time. That's part of the purpose of that problem. Now, you can do the integral on that one if you want to, but because it's not decreasing, then the integral test would not apply to that. All right? Okay, everybody okay with that? Okay, make sure that you always verify these conditions. That's important. Okay, let's go on and let's do one last one here. So again, with the divergence test, if we go ahead and do the divergence test on this one, okay, again, what we're going to do is we're going to do the limit as k goes to infinity of the sequence, which is k e to the negative 2k squared, like that. Okay, so if we look at this, this would end up being, let's say the limit as k goes to infinity of k, and I'm going to write that exponent as positive. So since that's a negative exponent, I could write this as k over e to the 2k squared power, like that. All right, so we got that. Now let's think about how we would do this limit. This is one that you want to be kind of careful on. Okay, when I look at this, when I think about this, first thing I know is the numerator is infinite, and so is the denominator, right? Okay, so since it's an infinity over infinity form, what is one approach you could take? L'Hopital's rule, right? You could, okay, which is what I'm going to do. So I'm going to go ahead and do L'Hopital's rule to do that. Okay, so when I do that, that just means, again, I'm going to do the derivative of top and derivative of bottom. So the derivative of k is going to be 1. Okay, I'm going to do the derivative, if we're doing e to the negative 2k squared, if I do the derivative of that, I'm going to get itself, okay, and then I'm going to do the derivative of the exponent, which is negative 4k, like that. Okay, so what that's going to give you then is that's going to give you negative 4k e to the negative 2k squared, like that. Okay, L'Hopital's rule comes in very handy on this problem then. So what you're going to end up having then is you'll have, I'm going to take this whole thing right here up to the top. So I'll end up having the limit of k goes to infinity of, let's see, that's going to be e to the positive 2k squared now, all over negative 4, like that then. Okay? So if you begin to kind of go through and look at that, let me make sure I got that derivative okay. I think I do.
Yeah, why wouldn't you just do...
What did I do? Oh, you know what I did? I did something stupid. Just absolutely stupid, okay? This is what happens when you stay up till 12:30 so that your students will get their test back. Okay, at least that's the excuse I'm going to give you, okay? All right, okay? I did something stupid, just really stupid, okay? So here's what you do, okay? All right, so here's the idea on this, okay? When we do L'Hopital's rule, we just do the derivative of the top and bottom. I don't need to change that thing like that. That was not a smart thing to do. So the derivative of k was 1. The derivative of the bottom is itself, e to the 2k squared times derivative of exponent like that. So what you would get is the limit as k goes to infinity of 1 over 4e 2k to the second like that. Okay, now that goes to 0, doesn't it? Okay, because the denominator is infinite. All right, so what that would mean is the divergence test, what we would get is that's inconclusive. Okay, so we don't know whether it diverges or converges. So anytime that the limit of the sequence is 0, then you don't have, the divergence test isn't going to give you a conclusion. So we do have to do the integral test on this. So let's verify that it's applicable. The function you're going to use is xe to the negative 2x squared, like that. Okay, that function is going to be continuous. The terms are going to be positive. You can go through and just kind of work that out and see that. And then on the decreasing on this, you could graph this on a calculator. I'm going to just kind of do that. I'm not going to do the calculus too much on that, just for a little bit of, for the time purpose on here. So if we do just x, this is a good thing to do because it verifies all the things you need to have. So I'm going to do e to the negative 2x squared. Do that in a standard window. I'm actually start the window like from 0 to 10 or something like that, just like the first 10 terms of the series. And let's see, I'll do something like, I'll start this way and see what it looks like. Okay, so that looks pretty good. Okay, if you were to go through and zoom in on this a little bit, you would find that all the terms are positive because they're always going to be above the x-axis. It does increase for a little bit, but once you're past 1, which is where the series begins anyway, you're going to decrease. Okay, so I'm going to just use the technology to kind of verify that, okay, on this problem without getting too technical with the calculus. Okay, so let's go ahead and crunch out the improper integral. So what we're going to do is we're going to do the limit as b goes to infinity of the function, or the integral from 1 to b, of xe to the negative 2x squared dx like that. So we're going to go ahead and basically we just got to work on the integral when we do this then. Okay, so this looks like a pretty good U-substitution integral. Okay, so let's see. What's a good thing to set u equal to in this problem? The exponent, right, because you want this thing to be like e to the u. You love it when you have the integral of e to the u. It's easy. Okay, so let's try that. See what you get. So we have negative 2x squared. Okay, du is going to be negative 4x dx. Divide by negative 4, you're going to have negative 1/4 du is equal to x dx. Oh, that's perfect. Okay, so that's what we have. Have an x dx there, so that thing is going to get absorbed by the substitution negative 1/4 du like that. Okay, what else do I need to do? Limits, don't forget. You don't have to, but it's a good idea to just go for it. Do it now, okay? Because we're going to have an easy integral. That's the point. Okay, so let's see. Start with the 1. So that's going to be negative 2 times 1 to the second. So that's negative 2. Okay, we're going to go to b. So the b is going to be negative 2b to the second. So we're going to change that limit to 2. And we're going to change that limit to negative 2b to the second like that. Okay? All right, so let's see where this leads us. We'll have the limit as b goes to infinity, the integral from 2 to negative 2b squared. Okay, and then that's going to be, we had, let's see, e to the u times negative 1/4 du. So that's all the substitutions in there. Okay?
Isn't it from negative 2 to negative 2?
What's that?
Isn't it from negative 2 to negative 2b squared? The limits?
Oh, yeah. Yeah, sorry. That right there is -2. Yeah, okay. That was supposed to be -2. Okay? All right, now we're ready to go, I think. All right, so let's see what we have. I'm going to pull out the -1/4. So I'll have -1/4. Then I'll have the limit. B goes to infinity. Nice integral, e to the u, evaluated from -2 to -2b squared, like that then. Okay, so what I'm going to have is -1/4, limit b goes to infinity. Now go ahead and evaluate it. So you're going to have e to the -2b squared minus e to the -2, like that then. Okay? All right, now before we do this, let's go ahead and make those negative exponents positive. So this is, I'm going to write -1/4, limit b goes to infinity of 1 over e to the positive 2b squared minus 1 over e squared, like that. All right, now we're ready to see what happens as b goes to infinity. So if you now go through and replace that b with infinity, you should be able in your head to kind of reason this out, okay? Because what you're technically doing is you're doing -1/4, and then you're multiplying that by the value of these limits. And you're really breaking this limit up into two limits in your head. So where does this one go? That's really 1 over infinity. So where does that go? 0. This is a constant. So what's the limit of 1 over e squared? Limit of a constant's a constant, right? So you end up with that. So that looks like what you're going to have is you're going to have -1/4 times -1 over e squared. So that's going to be 1 over 4e squared. Okay, that's finite. So what does that tell you? We converged, okay? So that means that since the improper integral converged, then we're going to draw the conclusion that that also converges. That's the idea. Problem done. Now, I'll ask you this question again, okay? Is the value of that series 1 over 4e to the second? The answer is not necessarily, okay? It could be. It's unlikely that it is, but don't jump to the conclusion that it is, okay? So that's the idea, okay? So notice with again, what you're doing in this section is almost everything you're doing is stuff you've learned in the past. You're kind of putting it all together. That's kind of the key, all right? All right, any question? So let's see. Let's do one more of these things that's got the integral test, and then we'll jump into a little bit different kind of an idea then, okay? All right, so let's see. Let's do the divergence test again on this. So let's do the limit. Okay, so let's do like the limits of the sequence. Okay, so we're going to do n goes to infinity, e to the 1 over n squared, like that. Okay, so if you kind of just, if you think about this a little bit, if you just think about if you looked at infinity, you would have e to the 1 over infinity squared. Okay, well, what's the 1 over infinity going to go to? That goes to 0, right? So what you'd end up having is like e to the 0 over something infinitely big. That's 1 over infinity, so that's going to go to 0, okay? All right, so that would mean then, again, the test is inconclusive because the value of that was equal to 0, okay? So the divergence test didn't do anything for us, but it's worth doing because it's pretty fast to do that, okay? All right, so now we want to go ahead and let's look at our functions. So we have e to the 1 over n, all over n squared, okay? Is this function always continuous? Now, n can't be 0, right? But does that matter? No. How come? Series starts at 1, okay? So we're good there, okay? We are continuous from 1 to infinity. That's all we care about, okay? So we're good there. Okay, the terms. Are the terms positive? Well, the way I would look at this is the denominator is always positive, right? 1 squared, 2 squared, 3 squared, 4 squared. How about the numerator? Is it always positive? You do e to any power. If you do any positive number to any power, it's always positive, right? So that means you really have a positive over a positive. So that means, yeah, it's positive. Okay, everybody with me on that? Okay, sometimes you just analyze that kind of in your head. Okay, decreasing on this one. Let's see on this one. I'm going to go ahead. I'm going to do the calculus. I want to do that one more time. Okay, so we're going to do calculus to determine this. Okay, you can look at technology, but you can't over-rely on it. But calculus, if you do this correctly, you can tell if the terms decrease. All right, yeah, we're going to go ahead and do that then. So let's see. The function is f of x equals e to the 1 over n, or let's do x. Change the variables. Okay, so e to the 1 over x, all over x squared like that. Okay, so we're going to do the derivative and a sign chart just one more time on this, just for a little bit more practice. So I'm going to do a quotient rule here, so that's going to be the bottom times derivative of the top. So you'd have that, and then you've got to multiply by the derivative of the exponent. 1 over x is x to the negative 1. So its derivative is negative 1 over x squared. Okay, like that. Then you want to do the top, e to the 1 over x, times derivative of bottom is going to be 2x. And that's going to be all over the bottom squared like that. So I want to kind of clean that up just for, do the sign chart and see if this function's decreasing the way we need it to decrease to do the integral test. Okay, so let's see, it looks like what you'd have is that would cancel, leaving negative e to the 1 over x, and then this would be minus 2 e to the 1 over x, and then all over x to the 4th power like that. Okay? Now what I'm going to do on this is we're going to try to find critical points on this that are within the bounds of the series. Okay, so what I'm going to do is set this equal to 0. And if you want to do this, if you're going to set this equal to 0, first thing is this derivative does not exist at 0. Everybody agree with that? Okay? The derivative's undefined at 0, but it doesn't matter. How come? Series starts at 1. So we don't have to worry about the fact that that derivative doesn't exist at 0. What we really need to do is see if we have any other critical point. So what I'm going to do is multiply both sides by x to the 4th. To get rid of the fraction, so that's going to be negative e to the 1 over x minus 2e to the 1 over x, whoops, is equal to 0. Okay, we're going to solve that equation to find a critical point. How do you solve that equation? Factor, right? You got a common factor, take it out, okay? You can either take the negative out or you can take the positive out. It doesn't make any difference. I'm going to take the negative out. That's kind of what I'm used to doing. So I'm going to take out that common factor, and that's going to leave me with this then. Okay, if we take that factor out, we're going to have, hold on, I don't even need to do that. You know what? Those are like terms, if you think about it. I'm just so used to factoring. Those are just like terms. So what you're going to have is negative 3 e to the 1 over x is equal to 0 like that then. And I think I made a mistake somewhere.
I think it's 2x.
2x. Oh, it's 2x e to the 1 over x.
Yeah, there we go. See, I'm just having one of my days today. Okay, so we got negative e to the 1 over x. Yeah, that was, I didn't bring the x down. Okay, so that's minus 2x e to the 1 over x equals 0. Now we're better. Okay, now we'll get an answer out of that. Okay, I tell that wasn't getting me anywhere. Okay, so anyway, these are, you do have to factor the e to the 1x out of that. So that's going to be 1, and then it's going to be plus 2x equals 0 like that. Okay, so now I think I'm good. All right, so what I want to do now is I want to set this factor equal to 0, and then I want to set this factor equal to 0 like that. Okay, so if I do this, let me ask you a question. Sometimes students don't see this very good. Does this equation right here have an answer to it? Is there any value that you could plug in for x that would make that equal to 0? Think about it. If you have e to a power, this is what you want, that pops up a lot of times. So if you have e to any power, will that ever be equal to 0? No, no way. No way, okay? If you take any positive number or any negative number and raise it to a power, you'll never get 0. Never. Okay? So that one doesn't have a solution. This one does. You can do this one in your head. Okay? You're in Calc 2 by now. You can do that in your head. That's negative 1/2, right? So that would be your critical point that you would have. So what we're going to end up doing on this then is we're going to do just kind of a little sign chart to show this then. I'll do this kind of at the side here. So we have the series. What you'll end up having on this then is you have a critical point of -1/2, but all we really care about is this, from 1 on out. So what you're going to find on this, if you did like what you did and learned how to do in Calc 1, what you would do is you would have a critical point at -1/2, but all we really care about for decreasing terms is what's happening 1 and beyond, like that. So you don't have to really waste your time going out on the rest of the sign chart. So we're not even going to care about that, and we don't even care about that. Okay, so let's just do that. So what we want to do is take the derivative, and you can take this form right here. This is your derivative right here. And we can just do a test value on that and see what happens. So I'm going to write that as, and you can even do this form if you want to. We have -e to the 1 over x minus 2xe to the 1 over x all over x to the 4th. Let's take like a test point, like something like 2, and see if it's positive or negative. If it's going to decrease, what are we hoping that it's equal to? Positive or negative? Negative. Okay, we know that if the derivative is negative, we're decreasing. Well, here's one thing I know. What's going to happen to the denominator? It's a 4th power, so what's that going to tell you? We're always positive, right? Okay, if you do 2 to the 4th, you get a positive number. What's going to happen on this, if you did like -e to the 1/2 minus 2 times 2, e to the 1/2, if you plug that in and calculated that, you would get a negative numerator, okay? I can tell by looking at that, because what you have is you have like terms. That's like -1 minus 4, so what that is that's -5e to the -1/2. So what you have is a negative over a positive, so we do have a negative, so that means we're decreasing, okay? Now, I do want you to know how to do that. You don't have to do that every single time when you're doing your homework, but don't forget that you can do that when needed, okay? So what we have is we do know that we're decreasing where we're interested in, okay? All right, I like to do that kind of as a review also. All right, now let's do the integral test because we know we can do that now. So what we want to go ahead and look at here is we're going to do the limit, again, as b goes to infinity of e to the 1 over x times x to the 2nd, and then we're going to do the integral from 1 to b like that, okay? So let's think about how we're going to do the integral. What do you think about this integral as far as a technique? U-substitution, what would be a good u? 1 over x. How do you know? E to the u, that's what you want, okay? All right, so don't go jumping into parts or anything like that. That part right there should be the u, okay? So when we go ahead and work that out, let's see, we're going to have u is equal to 1 over x, which is equal to x to the -1. So I want to have that, okay? du will be -x to the -2 dx. So that means du is -1 over x squared times dx like that. Okay, so notice if you look at this, we pretty well got everything we want. We have that x squared, and I forgot to put my dx there like that. Okay, so if you move this negative to the other side, you really get this. You have negative du is equal to 1 over x squared dx. Okay, like that. So this whole thing right there is going to get absorbed by negative du. Okay, now I'm going to work with changing the limits. I'm going to go ahead and do that. Okay, so let's work with that, and then we'll kind of put together our integral and see where this leads us then. Okay, so let's see. The lower limit is 1. The u-substitution is 1 over x. So you want to go ahead and do that. That would be 1 over 1. That's still 1. Okay, so that limit right there is going to stay 1. Do the b. What's that going to be? 1 over b. Okay, so you want to change that limit right there to 1 over b like that. Okay, that should be not a bad integral for you by now, hopefully. Okay, so let's see kind of what we have here. So we're going to have the limit as b goes to infinity we're going to go from 1 to 1 over b. Okay, we're going to have e to the u, and then the rest of it, dx over x squared, is negative du. So that's what we're ultimately going to work out to analyze whether this thing converges or diverges by the integral test. Okay, I can leave this, I can bring the negative out, so I'll have negative limit, b goes to infinity, the integral of e to the u is e to the u, then we're going to evaluate that from 1 to 1 over b. Okay, right, so that's going to leave me negative limit b goes to infinity of e to the 1 over b, and then minus e to the 1, like that. Okay, let's see kind of what we have going on this then. Okay, so if you go through now and plug in that infinity, this is what you'd have. You would have negative, it looks like that would be e to the 1 over infinity minus e. That e is a constant like that. Okay, so what happens to the 1 over infinity? Where does that go? Goes to 0. Okay, so we have negative e to the 0 minus e. So that's negative 1 minus e. What does that tell you? Converge or diverge? Definitely converge. That's finite, right? You got a finite value. That means that that's going to tell you that you converge. Okay, so that means since the improper integral converged, therefore the series also converges. That's how the integral test works. Okay? Okay, so we got one of our major tests kind of done now. That's the integral test, which you're going to use from time to time. Now, you don't always use the integral test. You know when you use the integral test? When the sequence is something that you can integrate. When if it's an easy integral, then it's a good methodology. Okay, but you're going to find a lot of series, you're not going to have a clue how to integrate them. So you got to go to some different test when you do that. All right, so tell me if there's any question about what we're doing with the integral test. Anything that you need me to clarify? Okay, we did several of those to kind of give you all the ideas that go through that. Make sure you follow this process. Always verify that it's doable, and then it's an improper integral. It's going to be all totally dependent on your integration skills, okay? Okay, so what we're going to do next is we're going to begin to look at something we call the P-series, and we're going to take a look at this type of series today. And what I'm going to end up doing with this one is the general P-series looks like this. Okay, this is what the series looks like. Okay, and P is any real number. So we're going to just kind of think about the convergence and divergence of this series a little bit. And I'll give you kind of what the key values are on this then. Okay, so basically let's see what happens if, and this is not supposed to be K is 1. That's supposed to say P is 1. Okay, so change that. Let's see what happens when P is 1. Okay, what you would have is you would have the series from K equals 1 to infinity of 1 over K to the first like that. Okay, well, let's write out the terms. So that would be 1 over 1 plus 1 over 2, 1 over 3, 1 over 4, blah, blah, blah. I don't know if you guys have even recognized that yet, but you might. Some of you might. Do you recognize that series? I taught it Monday. That's why I'm asking. Okay, what do we call that? Do you remember? Harmonic series, okay? I taught that to you, okay? And you'll start, once you get your homework and practice, you'll start getting on top of this. Okay, this is called the harmonic series. And do you guys remember what I said about the harmonic series? Converge or diverge? Maybe not yet, but you'll get it because you're going to have to. A harmonic series always diverges, okay? That one looks like it would converge, but it doesn't. This is the one I was telling you. There was a French philosopher back in the 1300s who proved that it diverged even before calculus existed. He did that 300 years before we even started developing calculus. But people were kind of looking at calculus ideas, even in the Greek civilization 2,000 years ago, but they just never developed calculus. If they did, we'd live in a totally different world. You ever thought about that? Because calculus changed the world, I mean, in a major way. So we might be like living in a different planet or something by now. I mean, if technology may have went, or we may be all dead. I don't know which. Okay, so that's the, but yes. So let's just be glad that we're here. So anyway, let's look at what happens on this p-series then. So it turns out that let's look at what happens if p is greater than 1. Okay, if p is greater than 1, then that p-series is going to converge. So what I'm going to do is I'm going to show you why that is the case. All right, so let's look at the integral from 1 to infinity of 1 over x to the p times dx like that. Let's just say p is some number that's bigger than 1. Okay, what will happen on this then is, and I'm just going to kind of give you an idea of how this goes without really doing a mathematical proof of this. Let's just say, for instance, that you were doing, let's start with like p equals 2. If you were doing the integral 1 to infinity of 1 over x to the second dx, okay? Now that's an easy integral, isn't it? You would be able to do that with ease. If you did the integral of 1 over x squared, that would end up giving you x to the negative 1 over negative 1. Okay, so this would end up just giving you the limit as x goes to infinity, or I'm sorry, b goes to infinity, 1 to b. I already did the integral, so I don't need to be doing that. I need to be doing the limit of this thing, which would be negative 1 over x like that. And I just want to do this on a couple of cases to give you the idea of what I'm trying to show you. Okay, so if you did that improper integral and you evaluated that from 1 to b, like that, that would end up giving you the limit as b goes to infinity of negative 1 over b minus negative 1 over 1. Okay, now let's kind of look at this and just think about what happens with this. Okay, first of all, you're going to end up, this part right here is going to be negative 1 over b plus 1. Okay, if b goes to infinity, what do you get out of that improper integral? You get 1. Everybody agree? If you do this, that's going to go to 0. 1 over infinity is 0. 0 plus 1 is 1. So the idea that I want you to get established without going through a proof is this. Okay, if you let p be a number bigger than 1, the integral test is going to give you something that converges, right? And if that converges, then what do you conclude about the series? It also converges, right? Okay. If we did the same thing for p equals 3, just think about this. The only difference if p was 3 is you'd have 1 over x to the third, which would be an easy integral. You would still end up getting something that converged. So if you went through and just kind of convinced yourself with a couple more numbers, 3, 4, and so forth, you're going to find the integral test is going to show you that the p-series converges whenever p is bigger than 1. Does that make any sense? Okay? So what you need to know is if p is 1, it's a harmonic series, so it diverges. But when p is bigger than 1, you're going to know that by the integral test, it's going to converge. Okay? Just memorize that and know that. That's a way to figure that out and reason it out. If you don't remember, it's just try a number. You're going to find on these tests that we learned, the big numbers are usually 0 and 1 has a lot to do with the convergence of a series. Okay? All right, so the other thing that we have is the p-series is going to diverge when p is less than or equal to 1, so you want to have that down as well. So I'm going to show you real quick why that is. So if you took the p-series and you did like the improper integral from 1 to infinity of 1 over x to the 1, okay, let's just say that p is equal to 1. Let's look what would happen on that improper integral. Okay, well that would end up being, if you did this integral, without going through all the details, you would be looking at the limit, b goes to infinity. What's the value of 1 over x's integral? ln of x, okay, then you would evaluate from 1 to b. What you would end up having is you would have the limit, b goes to infinity, of ln b minus ln 1. What happens on that one? If b is infinity, what do you get? Okay, that just gets infinite, doesn't it? So that diverges. Okay, so what you'd end up having is that would diverge. And you would find the same thing happens when p is less than 1. By a similar argument, you would have the same thing. okay? So if you had like, if you were looking at like integrals of like a negative number, okay, like if you, or even this, what if you did the p series 1 over x to the 0, okay, p being less than that? Well, that integral would end up just being the integral of 1, okay? But if you're doing an improper integral there, that would also diverge if you went through the details of doing that then. So the big thing that you want to get the handle on is the p series. You want to recognize it when it shows up, but the key thing is you want to know these things. It's going to converge when that happens, otherwise it diverges, okay? Because you're going to use that quite a bit as we further go through our study of series, okay? So that's the p series. Any question about that? Okay, to familiarize yourself with the p-series today, what we're going to do is we're going to determine the convergence of these different p-series here. So first of all, what you always got to look for is 1 over k to the p power. And then all you got to do is just think about what we just learned. If p is bigger than 1, we're going to know that it converges. Otherwise, it's going to diverge, okay? All right, that's a p-series. Everybody understand? 1 over k to the p. So this is a p-series with p being what? 10. P is the exponent. Okay, so what will happen is since p is greater than 1, 10 is greater than 1, what do you conclude? Convergence. Okay, that's what you get, okay? Okay, just get that down, study that. That's how you know the convergence and divergence of a p-series. Okay, it goes like that. So if you see you have one, it's actually super easy to tell whether it diverges or converges. P-series are easy. You don't have to do any test on it. Okay, now sometimes the p-series are kind of in disguise. So what I'm going to look at on this one, that doesn't look like a p-series. P-series is always 1 over k to the p, and p can be any real number. Any real number. Okay, so let's think about what we could do. We want to rewrite the standard form of the p-series. So what we're going to do is just change this. We're going to look at the series from k equals 2 to infinity. What's a simple algebra thing that you could do on that problem that might help us?
Multiplied by k to the negative 5.
How about if you had something like this? 2 to the third over 2 to the second. How do you do that? You do 2 to the 3 minus 2. You subtract the exponents, right? So what I'm going to do is I'm going to do that. I'm just going to do k to the e minus pi. Okay? Because what we're going to end up doing on that then is if you do that, now you want to look at the p-series. You want to change this to something with 1 over k to the p like that then when you do that. So the idea is you can do this like this. You want to end up having a 1 in the numerator and k to a power in the denominator. So you can go like this. If you bring that down, you would have 1 over k to the pi times k to the negative a, right? Okay, why am I doing that? Because I want it to say 1 over k to a power. That's why I'm doing that, okay? So now what? Well, I can add those exponents, right? Because if you have the bases are the same, you can add. So that would be the series k equals 2 to infinity of 1 over k to the pi plus negative e or pi minus e like that. Okay, and then that would be kind of the idea on that. All right, does everybody see where I'm going with this and why I'm doing what I'm doing? Okay, you want it to look like that. So what we have is now we see it's a p-series, and then p is what I highlighted. Okay, so what we would have is p is equal to pi minus e. That's what p is equal to. What do you have to do on a p-series? All you got to do is figure out that p is greater than 1. If it is, then it converges. Don't go jumping for your calculator. Pi is about 3.14. What's e? It's about 2.7 something. Okay, so that looks like it's a little bit less than 1, right? So what you would say is since p is less than 1, then you would say the series is going to diverge. Okay, that would be the idea. Okay, so again, it's all a matter of rearranging and looking at what the value of that exponent p is. That's how you make the decision. Okay? All right, see, it's not a very hard test to do. Okay? Now let's look at this next one and let's think about what you're trying to accomplish. Your goal on this problem is to have 1 over k to the p. All right, so tell me a couple things you do. What could you do to this 2? You take it out of the series, right? Just like you take constants out of integrals. You can do that. So you would have 2 times the series, k equals 1 to infinity. And what's a good idea to do with k to the negative 3/2? Put it in the bottom, make the exponent positive. Then you would end up having 1 over k to the 3/2 like that, okay? So tell me what the value of p is in this p series. 3/2, okay? That's why we did what we did, okay? All right. Now, what is the value of p? P is going to be equal to 3/2. That's greater than 1, right? So what's the answer? Converges, good. Okay, so it's all about taking p and see how it relates to 1. If it's bigger, it converges. Otherwise, it diverges like that. So those are some of the easier types of series to do. P series are easy. One of the easiest ones you'll ever learn how to do. Okay? All right? Okay, now what I was going to do today here is I was going to jump into 8.5. I'm going to do the stuff, this last stuff. I'm going to wait till Monday to do that. And there's a computer program I was going to show you that'll kind of help you understand this, and I couldn't get that working this morning. So I'm going to pause here